Coming at you again with number 6. This one is from the equation or the worksheet on conservation of energy, where there are some non-conservative forces, or there's some external forces out here that are changing the amount of energy in the system. Okay, that energy is not lost. It just goes somewhere else. It goes into some other form. Maybe it's heat. Maybe it's internal energy. Those molecules in there start moving faster, something like that. So number 6 says, how high on a hill can a car coast up if the work done by friction is negligible? Whoa, whoa, whoa. And the initial speed is 110 kilometers per hour. So let's answer that first. Sounds like a great idea. So at the beginning, so we've got a car that's going up a hill. Initially, it has some speed. That's 110, not meters per second, kilometers per hour. We're going to have to convert that, sadly. All right, so let's think about what would happen in the bar chart world. At the beginning, this thing has a pile of kinetic energy. And what is that kinetic energy? 1/2 mv squared. And so for this one, and it has no potential because it's on the ground, 1/2. The mass, we don't know, I don't think. Correct. Okay. For part A, we don't know the mass, which is fine. But we do know the velocity, 110, not really 110.
Teacher, please feel free to go to that.
We first have to convert between kilometers per hour to meters per second. So 110 kilometers per hour. We have to get rid of kilometers. The kilo in kilometers means 10 to the third, or 1,000 meters. And in 1 hour, there are 3,600 seconds. So basically what we're doing is dividing by 3.6. And you get 30.55. All right. We don't know the mass, but that is the kinetic energy term at the beginning. Okay, the fact that it says there's no friction and there's no motor on this, it's just gliding up the hill. That means there's no external work being done, which means the energy initial is just equal to the initial, or the energy final. All right, when it gets to its highest point, as it goes up the hill, we want to know how far it will get. What will happen when it gets to its furthest point? It won't have any more kinetic energy. This will be 0. So all that energy it used to have will now be potential energy. So what is potential energy? That's mgh. So this kinetic energy has to be equal in amount to this potential energy. So 1/2 m times 30.56 squared equals m times g times h. Still don't know the mass, but that's fine. Look, m's, we can divide both sides by m, and there it goes. Gravity is 9.8. Let's square that number. 466.8. Then we divide by 9.8. And we get the height equals 47.6 meters. And that's just pure height. So that's not from here to here. That is from here to here. 47.6. All right, good. That's what they said. So part B, continuing. If in actuality the 750 kilogram car with initial speed of blah is observed to coast up the hill, but it only goes 22 meters, how much thermal energy was generated by friction? Okay, that's how energy is dissipated through friction. If you rub your hands together, you feel them heat up. That's because friction generates heat. Okay, so part B says, in actuality, we don't have this perfect situation where all of that energy that was kinetic becomes potential. In reality, only some of it becomes potential because there's some work being done by friction that is negative, taking energy out of the system and putting it into heat. Okay, so how much? Well, energy initial plus the work done by friction, which is negative, is equal to the energy final. So energy initial, 1/2 the mass, they tell us now is 750, 30.56 squared, plus some work done by friction, we don't know how much yet, is equal to the energy final, not 1/2. It's potential energy at the end, mass, 750, times gravity, 9.8, times the height, which says instead of 47.6, this thing only goes up 22 meters. And now we just solve. This is 161,700. This is 350,116. So we see that the work done by friction, we just take this number and subtract 350,000. And I get negative 188,000. And I'm just going to round that off because I only need 3 significant digits. So 1.88 times 10 to the 5th, is that what they have here? Yay, look, good for us. And then it says, what is the average force of friction if the hill has a slope of 2.5 degrees above the horizontal? So that makes it considerably more difficult. So we already know what the friction work is. That's equal to the force of friction times the displacement, or the distance over which friction acts. So I'll switch to green for this last part. So this is a really gentle slope of 2.5 degrees, and we know that the height of that slope is 22 meters. So what is this distance? Again, the sine of the angle is equal to 22 over the distance. So the distance over which friction is able to act, 22 divided by the sine of 2.5 degrees. So that is a long 504.4 meters. And so that's what goes here for the distance. What does it say? What is the average force of friction? Okay. So we plug that in, 504. We're going to take this number, divide it by 504.4, and we get the average force of friction is negative 377 or 73.6 newtons, or 374 newtons, and it's down the hill. Remember that negative is just giving us directions. So the force of friction, 374, and my answer is right.